We have now sliced production frontiers in three different ways. In graph 12.1, we sliced production frontiers holding one of the inputs fixed and arrived at short-run production frontiers where the slopes of the frontiers were equal to the marginal product of the input that's being varied. In graph 12.3, we sliced the production frontier horizontally and arrived at maps of isoquants where the slopes of the isoquants were equal to the marginal technical rates of substitution. Finally, in graph 12.5, we sliced vertically along rays from the origin and discussed how this relates to whether the producer choice set is convex or non-convex. We'll now show that this notion of convexity of the producer choice set tells us something about whether the underlying production technology has increasing, decreasing, or constant returns to scale. We should note that if you want to explore further these three ways of slicing production frontiers, you should look at the Exploring Relationships animations for this chapter. We begin with three isoquants derived from a production frontier by slicing that frontier horizontally at 100 units of output, 150 units of output, and 180 units of output. We now insert a 45-degree line which represents the ray from the origin along which we vertically slice the production frontier in graph 12.5. That line intersects the blue isoquant at the input bundle 2 units of labor and 2 units of capital. When we double that input bundle to 4 units of labor and 4 units of capital, we notice that our output level increases from 100 to 150. In other words, by doubling the input, we less than doubled the output. If we add an additional 2 units of labor and an additional 2 units of capital, we increase the output from 150 to 180. Thus, when we added the first increment of 2 units of capital and 2 units of labor, we increased output by 50, and when we added the second increment, we increased it by only 30. Thus, we have a production technology that has decreasing returns to scale. The more we're producing, the less we're getting out as we increase both capital and labor by the same proportion. In panel B, we replicate the same shapes for isoquants, but we change the labels so that along the magenta and the green isoquants, production is higher than it was in panel A. We then insert the same 45-degree line that represents the ray from the origin along which we vertically slice the production frontier in graph 12.5. We now notice that when we go from the input bundle 2, 2 to 4, 4, output exactly doubles. And when we increase the input bundle by a further 2 units of labor and 2 units of capital, the output level goes up by another 100. So for each increment of 2 units of labor and 2 units of capital that we add, output increases by the same amount. We would therefore say that this production technology exhibits constant returns to scale. No matter where we're producing, we can always increase the inputs by the same proportion and get the same additional output increment as we do anywhere else. In panel C, we again draw the same shapes for the 3 isoquants, but we again change the labels on the magenta and the green to increase even further than they did in panel B. As we double the input level from 2, 2 to 4, 4, we now more than double the output, going from 100 to 250. When we then add 2 further units of labor and 2 further units of capital, we increase output at an even faster rate, going from 250 to 500. We would therefore say that the underlying production technology here has increasing returns to scale. As we increase the input bundles, we're getting more and more additional output the further up we go along the 45-degree line. We next want to get a sense of what that vertical slice along the 45-degree line that we took in graph 12.5 actually looks like in each of these three cases. We can do this because along the 45-degree line we're holding capital equal to labor, and so we can measure both on the horizontal axis. On the vertical axis we then measure output. Using 2 units of labor and capital results in 100 units of output. Using 4 results in 150 units of output. And using 6 results in 180 units of output. The shape we get for the vertical slice of the production frontier then takes on this concave shape. It starts steep and becomes shallower and shallower, because the more we produce, the harder it is to produce more by just increasing labor and capital by the same amount. We can use the same trick, noting again that along the 45-degree line capital is equal to labor, and therefore both can be measured on the horizontal axis. Had we used the ray from the origin other than the 45-degree line, we could also do this, except we wouldn't note capital equal to labor on the horizontal axis. We would note that capital is some constant fraction of labor. Using 2 units of capital and labor again results in 100 units of output, but using 4 of each results in 200 units of output, and using 6 of each results in 300 units of output. We therefore get a linear vertical slice of the production frontier along the 45-degree line. It's linear because it never becomes harder and it never becomes easier to produce more by adding additional increments of labor and capital together. Finally, we'll employ our trick one more time underneath panel C, again noting capital equal to labor on the horizontal axis, because capital is always equal to labor along the 45-degree line in the upper panel. Using 2 units of labor and 2 units of capital again results in 100 units of output, but using 4 of each results in 250 units, and using 6 of each results in 500 units. This creates a shape for the slice of the production frontier along the 45-degree line that starts shallow and becomes steeper and steeper as it gets easier and easier to produce by simply adding labor and capital jointly. Note that this shape is often called a convex shape of a function. A convex shape of a function is not the same as saying that the set underneath the function is a convex set. In fact, if the function is convex in its shape, as it is here, the set underneath is a non-convex set. And if the function is concave, as it is in panel D, the set of points underneath is a convex set. So if the vertical slice of the production frontier that we took in graph 12.5 takes on the shape that it has in panel D and gives rise to a convex set of points underneath, then the production frontier exhibits decreasing returns to scale. If it takes on a linear shape, as it does in panel E, the underlying production technology has constant returns to scale. And if it takes a shape such as that in panel F, a shape that starts shallow and becomes steeper and gives rise to a set of points underneath that's a non-convex set, then we have increasing returns to scale.